Okay, thanks to Ritu and Vicky and Manish for the invitation. Okay, so I will keep it general because I think the audience is very of different expertise. So I hope you like it. So this talk is more general than very specialized talk which I had yesterday and today, and I think it's very wonderful meeting for organizing it because we get to learn a lot of stuff. So I talk about CFD, but I will make use general remarks. So these are Moore's law. So this is a slide taken from this course slide. So presently we are at 200 petaflop, and we are supposed to reach exascale here sometime in 4 years or so, or very earlier. So the hardware has really progressed rapidly. It is I would say, core. I'm going to make the remark that the flops are free. So flops are basically going rapidly. But what about memory? So this is, in fact, this is the new processor by AMD. It has 32 cores in a single processor, and it seems like a very nice processor which we have just ordered. Hopefully we will try to test it. So if I put in one node 2 processors, in fact we can put 4, but 2 processors which we put, you can estimate the flops. So the 3 gigahertz is the maximum speed. So 3 times 8. This I didn't find in the internet, but I'm just estimating myself. So 24 operations per second, and I just multiply by 4 and the threads. So this is kind of very optimistic, but you can get 1.5 teraflop in this one, which is quite huge. Oh, sorry. Thank you. So now what about memory? So this is what by Chadai's talk. So first we will estimate how much data we need to do this operation. So I will just make it 1 teraflop. So for each floating point I need 8 bytes. So I need 8 terabytes among cache, RAM and so on. So this is like huge data I need to be processing every second. Now do I have that capability available now with RAM and cache and so on? So let's look at the data transfer. So I just took numbers from internet. I'm not really a computer scientist. So these are just rough numbers, but you'll see that problem is memory, just in line of what you were saying. So flops are free, data transfer is expensive. And so memory bandwidth is in that AMD processor is quite huge, 341 gigabytes per second, but it's still much slower than what we need. Like we need in terabytes. And if I look at the hard disk, it is much slower. We go down to 6 gigabytes per second. This is SSD hard disk, solid state hard disk. And if I look at the switch, band switch, which is the fastest we got, and this is an extreme number I picked. I mean, I'm not sure how expensive these switches are. So 200 gigabits per second. So it is basically 25 gigabytes per second. So we are basically limited by the memory flow, and that what affect the application which we work in, which is fast Fourier transform. I'll show you some complexity of parallelizing the software fast Fourier transform. So software challenges, these are hardware challenges, but as an application scientist, okay, we face this kind of. I'm just going to state some problems which we face in our institute, and I think it's generic. So for beginners. So this one problem is abundance. If you have just too many things, then we don't know what to choose. So, and also the level of complexity, like MPI, OpenMP, CUDA, ML, and the students said, well, it's too many things, I don't want to learn. So we find that real programmers who can use at least one of them too is rare in our institute. Okay? I mean, of course there are people who can write, but really advanced codes using huge number of processors are really, I mean, the number of students who can do it is not very high, and leads to confusion and non-start. Then structured programming like C++, the physics won't know mostly. So they're basically in computer science, and the physics still now, I mean till now, people teach Fortran most often. So this is because structured programming becomes a problem. And pressure to publish. So we have to do physics rather than publish in computer journals, and then it becomes a big problem for big software development. And to scaling and so on, it takes decades. Sometimes I would say that CS2s are too complicated for me to understand. So they are, of course, very clever algorithms. I'm really flabbergasted sometimes by the cleverness of those algorithms. But that makes it complicated for people in physics to implement them. Now for advanced users, optimized use of hardware. I think some of the hardwares are just too complicated. I mean, to make use, for example, the switch. I want to use the switch optimally, and then it just schedulers. We need to really, which node should talk to which node, and which my student who is very good is trying to do it, Anand Chatterjee. So optimized use of hardware, I think, is a challenge, and we need some kind of framework to talk and clever ideas. Structured programming. I'm going to show some design of our code. I believe structured programming is very, very critical, because I'm told that the problem is not the hardware, but problem is the programmer's time. Is that correct? I mean, this is the thing I'm quoted often. So, programmer, you have to really pay a lot of money for making a good software. So, you should make a software which is usable and can do more things. And keeping up with upgrades. For example, now the MK3, our code works with MK2. Now, this will require something like 1 month of work. Code the whole code. Then somebody says, well, why not use vector processor? So compiler optimization. So this is quite a challenge for users in scientific application. You have to keep up to date almost every 6 months. I mean, the processors keep changing every 6 months. So all that idea and optimization. So this becomes, and this is an issue. And interaction with users plus programmers. So users, most often you find that they want the code should run, and so basically they make some change in parameter and the code breaks, and they're basically very annoyed and things like that. So these are challenges which we have in scientific applications. So let's now look at CFD and why it is important. So by the way, it is also called colorful fluid dynamics, C for color. So of course you have drawn nice plots. I don't have here, but you'll find very lot of colorful plots, which Guru showed some of it, but it's not CFD, but it's kind of CFD. So major application is weather prediction. I mean, for me, I think this is critical, especially in India. We really don't have very good software to predict weather and climate modeling. And aeroplane and cars, they are really huge, use a lot of HPC. Defense, offense, whatever you can call. So missile design requires a lot of HPC. And this engineering application, turbines and so on. So this is, and astrophysical flows, black hole for example, the gravitational wave, the hardware was very important, but the software was equally important. So they simulated two black holes colliding with each other, and they compared. In fact, it was all a lot of data analysis. And theoretical understanding. So I am basically here. So we try to make model of turbulence, and that requires a big simulation. So one example I am going to show you, which is very nice, which uses in fact spectral code. So magnetic field of the Earth flips around. Well, it is random, but it could be million years, or it could be 200,000 years, or it could be even 50,000 years. So it has flipped in the past, and people wanted to understand why. So they solved. This is called magnetohydrodynamics. So magnetic field plus hydrodynamics is the equation. And I'm going to show you the simulation done by Glatzmeyer in 1995 and Roberts. So this became really highly exciting because the equations could reproduce what happened in the past. So please look at it. So this north is yellow and blue is south. And it's turning, it's this flip. So now we see that south has. So this, yes.
So what is the time scale of this switching?
So it's around 5,000 years. That's a rough number.
And in between, so what will happen to things? Which
yes. So you can see here, it doesn't remain dipole. I mean, of course, Earth's magnetic field is not dipolar. Dipole plus quadrupole, I mean there are and higher poles, but it's probably dipole right now. But when during the reversal, it being quadrupole will become important. So we'll probably start. Well, we'll start getting cosmic rays coming on equator or anywhere actually. It's random. So cosmic rays are right now coming in the north and south poles. but they will come everywhere. So that kind of, so it's essentially quadrupolar and higher moments. Now, so we did the simulation with not our code, but the spectral code 11 code. So this is in convection, so hot below, cold above, and you can see the field is going like this. The arrows may not be visible, but it's a roll in convection, hitting from bottom, you see, but it's not quite rolls in textbooks. Huh? Now please see what happens. So it's reversed, no? You saw that? So it was going one way like this, now it is going, earlier it was counterclockwise, it was clockwise. So we find that similar phenomena in convection as well. In fact, the dynamics, if you look at mathematically in terms of Fourier modes, there are a lot of similarities, yes? Parameter? It's a 2D Rayleigh number around 10 power 8 or 10 power 7. So it's a turbulence regime of in convection.
You see it in 3D also?
Yeah, 3D also has reversal. Okay, now let's look at the methods in CFD. So there are large number of tools, methods actually, and they're all different. So in fact, Guru pointed out that we have finite difference and spectral, right, and finite element. I think he did mention that. And this is like in real space, you make a discrete grid, and we solve this partial differential equation. So you need to compute derivatives. And derivative is you need basically Newton's prescription, fx plus dx minus fx divided by delta x. Now this is what is done in finite difference. So difference is finite into it, and finite volume, finite element are slightly different, but they're all real space discretization. But spectral is in Fourier space. Now question is, why spectral? No, I have a different take. So I think you said that okay, derivatives are calculations are precise, which is good, which I agree completely. But spectral also gives an idea that it's multi-scale phenomenon. So if I look at, so wave, you know, this one wave, then wave it, smaller wave and smaller wave and smaller waves is basically giving us a prescription in different scales. So example could be wealth distribution in a country. So we have wealth at a big national level, then district level. So there is and the money is flowing from one scale to other scale. And that flow is captured very nicely in multi-scale physics, and that's captured in Fourier method. And Fourier is not the only method that you can use any kind of basis function which is multi-scale. So in spherical geometry you use Legendre polynomials, or in engineering they use multi-grid method. Multi-grid method is basically you involve grids at different levels, or they call GMR, no, adaptive mesh refinement. We are using multi-scale, so it is a very generic issue, but Fourier is very mathematically done by Fourier 200 years back. Okay? I mean, I owe a lot to Fourier for all this work, and it's still very nice, and you can get this ideas about multi-scale energy transfers, in fact money flow too. So money flow should not be seen as going from one person to other person like in real space, it's going from one scale to other scale. And then it's nice to make models for that. So we do same thing in energy, in fluid too. So fluid, this Kolmogorov theory is very important theory, which is energy going from large scale to small scale. And that is understood nicely in Fourier. So I just want to say that it gives you a different perspective. So this is the equation. It's called Navier-Stokes equation. We use the velocity field, and nu is this is a dissipation term. It kills the velocity field and P is pressure. Okay, so this is what I need to solve. Now, so we can do for understanding multi-scale phenomena of fluid, we can use spectral. Another thing is whether people, of course, give the argument that it is accurate. And the reason why, so I think I'm going to explain this in more, just one more equation. So this is a Fourier transform. So f of x is written as sum of Fourier, this is the Fourier amplitude, and e to the power ikx. Okay, this is the definition. So we sum over all, this is 1D, so I'm summing over various wave numbers, or various like sin x, sin 2x, sin 3x, this is what it is. Now if I want to take the derivative of f of x, one idea is like finite difference, you take 2 points and take the difference and divide by delta x. But there's error, right? There's error expansion, I have truncated it. But in Fourier, it's just, in fact, it's exact. What do? I just take the derivative of this one, so I just need to multiply by ikx, which he mentioned it, but I'm just showing you it's so easy. So given Fourier amplitude, I can multiply by ik and do the inverse transform. If I have resolved all the scales of the problem, then my derivative is exact. Of course, it requires that you resolve all the fluctuation, and that is required for, that is a challenge. For a lot of, highly fluctuating system like Earth weather system, we need this kx to be huge. In fact, we can estimate it's going to be terabytes of data, more than terabytes of data, even if you use a very coarse grain. So, but this is exact if you can resolve all the grid points. Okay? So this is the idea. So how do I solve in Fourier space? So you have to think not in real space but in Fourier space. It's a bit of thinking differently, but you have to get used to it that my u is not in real space but u is amplitude, that Fourier amplitude, and the nonlinear term is going to be product, Fourier transform of the product. And this k is coming from the gradient. No? There's a gradient, so k is coming. So please remember that I had u dot grad u, so there's a product. So product, if I do Fourier transform, then in mathematics you recall, it becomes a convolution, and convolution is order n squared, if n is the grid point. And n squared is very expensive if n already is too large. So 10 power 12 will give 10 power 24, which you can't fit anywhere. It's just impossible. So Steve Orzov, many years back, he gave the idea for hydro that we can use FFT for this. And how do I do FFT? So I'm using u of k. So I go to real space by FFT, which is n log n, not n squared. So I go to real space and multiply and come back to Fourier space. So it is done in n log n rather than n squared. And FFT is fast Fourier transform, not the usual Fourier transform which I wrote there. And again, it's based on multi-scale. If you look at FFT algorithm, it's even data, odd data, even data, odd data. It does in a structure, tree structure. And so we solve multi-scale problem, and you are able to do it in n log n. And so this is how it is solved. So this is called pseudo spectral. It's not called fully spectral. It's pseudo. Sometime I go back in real space, and it turns out that sometime is 80% of the time. So in this method, the the maximum time is taken by Fourier transform. So time advance, I'm just stating it, but Euler scheme, you can go from the data at time t to time t plus delta t. I should write t here. So I can just time advance. It's straightforward Euler scheme. And I'll skip this part, it's technical. So nonlinear computation, this is what I said. From u of k, you could go to real space by inverse Fourier transform, multiply. So this is n log n, but this is n, because I'm doing multiplication locally every grid point. And then I do the Fourier transform and then multiply by ik. So these guys, FFT and the inverse FFT take n log n, and multiplication is n. So multiplication is cheap, no problem, it's very easy. But complexity is in FFT. And so I'm going to just describe about FFT. So Fourier transform in spectral code typically takes 2/3 of the computer time. Depends on the code structure and so on, but 80%, 70% is the time taken by this. So we have this code. There are of course many spectral codes. So like there are probably 100 spectral codes in the world. Some are well known, but I'm going to talk about our code. So we call it Tarang. It's a wave. In fact, if you know Sanskrit, it's a Hindi or it's like Tarang is wave. So it's motivated by Orzov's idea. But so I will also tell a little bit about the design. You have single code to do many different kinds of fluids. So this is a PDE solver, partial differential solver, using spectral method. So we can solve turbulence problem, instability problem. Of course, we require periodic boundary condition or free slip boundary condition. So boundary condition cannot be arbitrary. We can also do no slip, but that requires more complicated basis function, which we have not done it yet. So we went up to this one, 6144. The record right now is 8,000 cube. So we are still not, we are below that. The Japanese group has gone up to, now they're trying 12,000. Okay, so, but this was maximum we can fit in Sine, which is in KAUST, King Abdullah University. And this is what we could do. So we ran up to 2 lakh processors. So 196,000, so 0.2 million, that is what approximately 0.2 million. And this is 3 times 2 to the power, 3 times 64,000. So it is not multiplied 2 power n, but it's 3 times that. And this is open source, you can download from this Turbulence Hub. So this is a hub we thought we'll probably bring in from all the people working in Turbulence. We have not managed it yet, but hopefully in future we'll be able to collaborate through this hub. So this appeared in JPDC, Journal of Parallel and Distributed Computing. So as I said, this can do lots of physics problems, and just for students or for developers, maintaining a single code is much easier than maintaining n codes. N could be even 2 or 3, right? So in typical turbulence groups, say one code will do fluid, other code will do MSD, other code will do rotating. So every student has a code. And of course, you make a change here, then that will not reflect here, right? Because suppose I do I/O parallel I/O, which is significant time, which Vipin was telling, and but then you have to reflect everywhere. So it's best to have one code, and if you structure properly, it's possible that we can do single code. In fact, we can do your problem with our code. So I'll show you how it can be done. Of course, it's more work, but in 2 weeks I can assure you that it can be done. So it's objects, you're very confident that I have these objects. We can. So I don't think of velocity field as 3 arrays. I think of that velocity field as an object of velocity field, and then it's easy to think and manipulate and get the result. And as I said, it can do instabilities. These are specific to experts, but we can do all of it in the code. As I said, free step, but these are things which it has become to-do list for 10 years now. So after some time, the energy is lost, and we are not able to make progress in this. It can also do, as I said, energy flux is multi-scale energy transfer. It is, so most people report spectrum in literature if you are doing CFD, but very few people report flux. And we can easily compute it using spectral method, but unfortunately just people don't report it. And it's just that they didn't code it. And so I think it's important to use different diagnostics. And these are different diagnostics. These are specific to our field. So we went up to this way. So I just want to spend a little bit of time on maybe inspire some students, so should think don't start coding. That is what I would say. So in fact, I spent 1 year just to think of the design, how we should design. And we broke the code around 30 times. But it has become somewhat stable. But still, I think we need to break it further. But so in fact, you can do various basis function. So my function is basis independent. So what I mean by this is, so I want to compute this u dot grad u. So grad is a gradient operator. It's like d by dx, d by dy. So this one I want to do, and somebody says, well, I want to do b dot grad u. So b is a magnetic field. You see, these are not same operations, right? But I want also do for periodic boundary condition as well as with one wall. So the person, so I say, well, I will still use the same function, compute n length, but behind the scene, I need the Fourier transform, but my Fourier transform can be doing either, so I call this function Fourier transform, but it is its job, the function job, to call FFF, the Fourier in all 3 directions, or with one wall. S is for wall, okay, sign. So it is internal. So the person who is looking at this code, he says, well, let this be offloaded to the, like for example, you offload to GPU some work. You say, well, this function for Fourier transform, let it decide which basis function or which kind of elementary function it is working with. So it is abstracted at different levels of objects. So our Fourier transform has all these possibilities by choosing different kind of walls, but you call the same transform. You don't call something else. Your array goes in there and it will do for that particular basis. But of course, for each of them you have functions. But the user at the outside doesn't know what is being done internally. For it, give the basis function and give the transform, it will do it for that basis function. So this is for us is a parameter. So it is very useful to design that way. In fact, periodic boundary condition as well as with one wall or 2 walls, like these 2 walls and with Chebyshev, it should be the same. This function does not change. Compute n does not change. It remains the same. And also, one more point is that I give the same name to u dot grad u as well as u dot grad u. This is possible with C++. It's called function overloading. You can use the same name for different operations or different function, different arrays. Just you can use that, and this is possible. So C++ or object-oriented programming helps in designing this general purpose solvers. And so it's basically general PD, and you can use this for solving different kind of physics. So for me, for MHD, you have two fields, velocity field and magnetic field. So I just create two objects, which is one vector field, which is U, other vector field B. Now for temperature, velocity field U and temperature field T, which is scalar. And then it will do all of it. So we just have to use as a parameter rather than rewrite the whole code. So these are the classes. I mean, this is universal function which has different basis functions. So these are basis functions. And my student Ananda was very clever, and he had clever ideas of C++. So these are class structures, okay? So which came from Doxygen, it generates them. So we could do it. This is called virtual function. This was used here. So virtual function is that you don't tell. So first, either it is Fourier or sine. It will be known later when it is required. We don't tell right now. Well, we will do it. We relax, but behind the scene we'll do it. So this is called virtual function. So which was useful for designing this one. So now I'm coming to parallelization. So I just want to say that I think design well. I mean, these codes which are general or which probably should last longer should be designed well. So parallelization. So there are three tasks which require parallelization, which is spectral. I mean Fourier transforms. So I said that I need to go back and forth in real space. Then multiplication, which is trivial. I mean, I don't need to say. And input output. I think Bipin did point out. It can take huge amount of time. You have terabytes of data, and if I don't do parallel input output, it can take long time. But we just offloaded it. SDF5 is very nice, and for us, I think we are quite confident. I mean, we are doing in CDAC UR, and this was, in fact, a lot of work was started in CDAC. This speed up. So SDF5 we are testing, and I think it took approximately half an hour for read write. At that time for 3000 cube of that code. We just filled up your whole machine. We used to break, we were testing here in 2012, I think. The whole machine used to just shut down because it was running on the whole machine, and so it had to be. But this one is quite nice. So one more thing, that if library exists, use it. So we use something called Drift library, which is very nice. In fact, Santosh has improved Drift libraries for array operations. In fact, Fortran is faster for usual array operations with C++, in fact much faster. But the libraries like Blitz or Boost library, they improve the performance of the arrays. So I mean, I just want to make them. I mean, see, in computer science, they want to work with integers, right? I mean, like graphs and so on. So the C itself is not very well optimized for floating point, or at least C++. It's true actually. The array operations are very slow. So I mean, computer science, we need some help. You should also kind of do some support for floating point operations. So of course, people write this libraries which work on top of it. So, but that's a problem which we face with modern languages. So I just want to say how much time I got. I think 10 minutes. 10 minutes. So FSC parallelization is the following. So we look at 3D. Okay. So now you can see that this is exponential, but I have three sums, kx, ky, kz. So I have to go from Fourier space to real space. So three sums are to be performed, and you can easily see that for big data size, you can't fit in a single processor. So we divide the data among different processors. And one more point is that we should divide it equally. So this is called load balancing. So if you don't divide equally, the weakest guy will determine the time. So it requires all processors are equally smart. If anything is the weak guy will slow down. And the work also should be divided equally. So we divide the work equally. So this is called slab decomposition. This was done first. Well, I mean, I'm sure other people have done it, but most famous software for FFT is FFTW, fastest Fourier transform in West, done by MIT. And so it divides the data among 4 processors. It You can see it's a slabs, So this is full data, but I divided among 4 processes, 0, 1, 2, 3. Now what is done in FFT is that I have to do sum along x and sum along y, sum along x and z, right? I can call this x-axis and this z-axis. So I can sum over this slab internally. This processor, the ping processor, has all the data for x and z. So it can do the sum along x and z easily, no problem. But when it tries to do the y direction sum, it cannot. Because along y, it has to get data from green and blue. No? So along y direction, it can't do the sum. So then we need to do some data transfer. Now see that if I need the data along this direction, I need the data from all the 4 processes. So this is called all-to-all. In fact, everybody will need data from everybody. So finally, so what is desirable is that I get into this configuration where I have y and z. So my data now is divided along x. But I have to go from here to there. So they will be transferred among all of them to reach here. And this is called all-to-all transformation. So this is also called matrix transpose. And it is achieved in that. But this is a basically the most time-consuming task in FFT. Because it has to talk across nodes and across processes. So I'm going to show you the numbers, which are very surprising, but I will just show you after explaining. So we did some called transpose free. So one thing is the matrix transpose has more time, takes more time. I will not go into details, but we can use something called MPI vector and consecutive data transfer in MPI, and it turns out that it saves around 10% time. So if I did transpose, then I have to do this transpose, transfer, then transpose again. But we don't do it by this function, which is quite nice function, MPI vector. And then you can see that its order remains 1, 2, 5, 6. This is 1, 2, 5, 6. Then 3, 4. But my process 0, it is like this now. 0, 0 has become that. So it's possible to do with sophisticated MPI functions. We could do it, and it has gives speed up, but not very, very significant. But 10% is good. Now, it turns out what is the limitation of this slab decomposition? It has a strong limitation that if I have n cube data, then I can use only maximum n processors, right? The number of slabs I can make, or number of planes I can make is n. Now, if I do 4000 cube, I will be told, okay, when I use only 4000 processors, I will be, in fact, abused. You will say, well, you should use 64,000 or 32,000. So you should say, well, you want to use more cores. And then we can't, you have to go beyond K50W or beyond A50 slab decomposition. So idea is to do this called pencil decomposition. It was done first by Dimitri in San Diego, and it is called P3D FFT. That was done, I think, around 15 years or 20 years back, or around that time.
Not that long.
Not that long, okay. So around a decade back, he did this work. And so basically now we can make, you can see the division now, instead of slabs, I have towers, like this Manhattan towers. In principle, I can go to n square towers, right? Each column is one column, one data thing. So now you can use, in principle, n square processors. So it turns out you can use more processors with it. So how do I do with pencil decomposition? So now here I can do FFT along one direction for all these slabs. So this okay, so I can do along this. Then I have to transfer the data along. Now I can't do along this, so I have to now do the transfer. Then I have to do along that. So it turns out that we have one more transfer. But it turns out that you can transfer not along all the processes, they can transfer along a bunch of processes. That saves time. And so we implement this. So this was done by FFT scaling, which was on Sahin. So you can see that we can get, it's linear in log scale. It's not really linear in real space. But communication is n to the power 0.7. Okay. So not linear, but computation, T inverse computation is T to the power 1. So we get around 0.7. It is not linear, but this implemented is called FFTK, FFT Kanpur. So it works. So thorough scaling quickly. So you can put this in our big code, spectral code, fluid solver, and it can also go. So these are called weak scaling and strong scaling. But it is kind of, you can use more processors up to 2 lakhs. We are not very confident that it will scale, but it does scale. So we can go probably higher. I don't know. I mean, this is now this is. It turns out that we can basically maximum performance by how much we are getting. You can estimate the number is 1%. So you can imagine that 99% is basically going across for communication. For Blue Gene it was better, which is older machine. The reason why it was better was quite revealing. Here the processor is slow and your communication is slow. But here processor become fast, so communication has speeded up but not so much. And that made it, so new machine does not mean that you'll get it's better performance but not optimal performance. Now, so basically GPU we didn't really get very much because of again communication. So FFT with like 4 GPUs, boom, it comes down. Unless we have NVLink and so on. So I think I will stop. So like finite difference is what probably will be better for 1 million processors or more. So FFT should scale at some point, but we don't know when. But so I think I'll stop. Thank you.
We have time for 2 quick questions.
Hi, Professor. Nice talk. It's a great tool to have. So, like, I was wondering, when you perform these pseudo-spectral operations, how do you handle problems like aliasing and those kind of?
Okay, aliasing is very easy. So you truncate n data to n by 2 by 3 n.
Okay, so you use the 2 by 3
rule.
Yeah, okay, does it happen automatically in the FFTW thing, or you need to do it?
No, you have to do it yourself. So this was zero padding.
Okay.
So you just zero the higher part,
additional ones,
and then FFT will come back. So aliasing is straightforward. 2 by 3 rule.
Okay.
You had a question, answer.
So, would you consider adding wrappers in Python?
So-
you mentioned that it's difficult for some people to learn all these programming languages, and some of them just want to run a case which may have already the basic infrastructure for.
Yeah. So it's true that, for example, we have a lot of data from ocean data. So they wanted to use how to compute flux, energy flux, and the spectrum and so on. So my student did create a Python for post-processing. So I think Python is very useful tool. It's slow, but possibly with TensorFlow or new tools like Google and Facebook and so on, it may become faster. So I think we are exploring it. It's, I think, very exciting, but it requires again an investor of time.
Thank you, Dr. Verma.
Okay.